So now till now we have seen what are distribution and density functions. So today we are going to see a special kind of a density function. Okay. So we'll be seeing both the density as well as distribution of some special kind of variables which are known as Gaussian random variables. Okay. So yeah. So this is the outline of today's session. So we'll see what is a Gaussian density function. Okay, so and then we'll see what is a Gaussian distribution function, and then we'll be seeing what is a normalized Gaussian distribution function. Okay, so any random variable which has a particular type of function, it is called as a Gaussian. It is said to have a Gaussian density. Okay, so actually this densities and distribution, they refer to some kind of a random variable, right? So this particular random variable, it is called a Gaussian density or a Gaussian distribution. Okay. So this is the introduction to Gaussian density function. So we say a random variable x is having a Gaussian density, or it is a Gaussian random variable whenever it has a density function of the form that is shown here. Okay, so you can see a very elaborate function here. Okay. I'm not able to have a right click. Okay. So as you can see a function fx of x. Okay, so that is known as the Gaussian density. My laptop was slow down. Okay, so that is the Gaussian density. Okay, so you can see there are a lot of parameters here. So the function is defined as 1 by root of 2 pi sigma x square. Okay, so this is a sigma suffix x. Okay, so this is a particular constant. Okay, which is multiplied by an exponential term e power minus of x minus ax the whole square by 2 sigma x square. Okay, so this particular function, okay, so this entire function, this is called the Gaussian function. Okay, this is called a general Gaussian function. Okay, so you are seeing lot of terms. So for now, don't worry about the terms. We'll see what it actually means. Okay, so one more condition is stated here that these are some constants. Okay, sigma x is a particular constant, and then this ax is another particular constant. Okay, so there are only two constants here, sigma x and ax. Again, the sigma x is repeated here, right? So this is the entire thing is called the Gaussian function. Okay, so since all the things are constants, it is just a function of x. Okay, so the variable x appears only here at this point in the exponential. Okay, so the sigma is a constant which is greater than 0. Again, ax is a constant which can lie between minus infinity and plus infinity, and both are real numbers. Okay, so this is how the Gaussian function is defined. And any random variable which has a density of this form, the form that is shown circled in the yellow line, so that kind of a random variable is called a Gaussian random variable. Okay, so again, the Gaussian random variable is a continuous random variable. Okay, so we have seen in the first class there are two different types of random variables. One is the continuous random variable, other is a discrete random variable. So the Gaussian random variable is a continuous random variable. Okay, it is defined on a continuous sample space. Okay, so this is an alternate form of the same function. Only thing here is I have rewritten the exponential in a more clear and legible way. Okay, so here the exponential is you have given terms in power of e. So here I have just expanded. I have just written it more easily readable form. Okay, so this is an alternative form of the Gaussian function. Okay, so now we have to see how does it look like. Okay, so how to visualize this Gaussian function. Okay. So if we plot this function, that is fx of x, that is the small fx of x, if we plot it, how does it look like? So that is what is our question. Okay, so how does it look like if we plot? Okay, so if you see in the previous slide, it is a very complex function, right? So this complex function, we have to, if you want to understand this complex function, we have to understand it part by part. Okay, so that is why I am showing this graph. Okay, so I am showing this function. So we are considering a very simple function, g of x. Okay, so g of x is equal to e power minus x square by 2. Okay, so it is an exponential. It's an exponential function where the exponent is negative of x square by 2, right? So first we'll consider this exponential, how does it behave? That is the exponent. Okay, so we are just going to plot only the exponent alone, and we are not going to consider the negative sign, and then we are just going to plot the exponent. Okay, so how does the exponent look like? It is a quadratic function, right? It is x square by 2 is a quadratic function. So obviously it is a parabolic function, right? It gives a parabola. If we plot it, it gives a parabola. Right now, what we are doing is actually we are using these numbers. Okay, so whatever number we are getting in the parabola, those numbers we are raising to the power of e. Okay, so say for example at -1, it has a value of, so near -1 it has this value. Okay, so maybe near +1 it has a value of say 0.5. Okay, here it has 0.5. Okay, so at a different value, say -2. Okay, so it is having a value of, so maybe it is still higher. So at each point in x-axis it has a corresponding value, right? So this is the corresponding value. Okay, so now these values we are putting in the power of e, right? We are putting as a power of e. So what will happen? So definitely the when we raise some positive, all these numbers are positive numbers, right? So all these values are positive values. So when you raise a positive, means when you raise e power some positive value, so definitely you will get more bigger positive values, right? So but what we are having here, we are having a negative sign here. Okay, so what we are actually doing is we are putting 1 by e power some positive constant. Okay, some say some constant is there, say e power x. So this is positive, this is great, something that is greater than 0. So how does this behave? How does this entire function behave when this constant is kept on increasing? So how does this entire function behave? So it is in the e power is in the denominator, so the entire function decreases very fast, right? So the exponential, if it is in the numerator, it increases, the values are increased at a very fast rate. So now the exponential is in the denominator, the value decreases at a very fast rate. By rate, what I mean is along the x-axis. If we move along the x-axis, so the rate at which the function comes near 0 is very fast. Okay, so you'll have some function which is decaying very fast like this, and on the other side also it decays very fast like this. Okay, so that is how we arrive at the visual form of the Gaussian density function. Okay, so I have just given the plot. Okay, so okay, now what we have done is we are just we have first plotted h of x, which is nothing but a quadratic equation which has a parabolic form, and now we are raising h of x to the power of e, right? So how, what kind of plot we'll get? So we'll get a exponential, we'll get the Gaussian plot. Okay, so you can see a bell-shaped curve here. So that bell-shaped curve is the visual form of the Gaussian plot. Okay, I'm just making it clear. So here you have a bell-shaped curve. Okay, so that bell-shaped curve is the general form of a Gaussian density function. Okay, so how we obtained it? We first had a quadratic equation and then we raised that to the power of e. So we get this function which is decreasing very fast because of this denominator term. Okay, okay. So hope you understood this. If you have any doubt, you can stop and ask me anytime. Okay. So now, if you go back to our actual function, so it is not a simple exponential function. Okay, you can observe that there is a particular kind of shift present here. Okay, so we have some term that is getting subtracted from x, right? So just now whatever we saw as a graphical form, it is just x square by 2, right? So now we are having some term, some constant which is getting subtracted from x. Also we are having some denominator term here in the exponent. Okay, so we'll see how to include those terms. Okay, So yeah. Yes. So this was our previous Gaussian function. So you have a function g of x. Okay. So now we are making some subtraction from x. So what does that represent? See, you have some function g of x, and then you are introducing a shift in x. Right. So what does that make? It creates a shift in the function. Right. So the entire function is shifted to the point where ax is lying. Okay. So for example, I'm showing a plot where the constant term ax takes a value of 5. Okay. So what happens to this graph? Whatever we see here, okay, so the entire graph shifts to the point 5, right? So whatever occurs at 0, that now will occur at the x-axis value of 5. Okay. So here at 0, what happens in the graph? Okay, so you can see the graph reaches a peak value at 0. Okay, so for x minus ax, okay, when ax equal to 5, what happens? This entire graph shifts towards the right. Okay, and then it reaches where maybe here you have a 5. Okay, so this entire graph is shifted to this point. Okay, so at 5 you have a peaking occurring. Okay, so you have a peak occurring at 5. Okay, so that is how we have to interpret this x minus ax. So instead of 5, if we generally represent that by ax, so the entire graph moves to the point where ax is located, right? So now you can visualize this. I have just given a graphical representation for ax equal to 5. Yeah. So now you can see the x-axis values, they have shifted to 5. Right. So you can see the x-axis value, now it is 5. So the peak is now occurring at a value of 5. Okay. So now what we are going to do, we are going to introduce some term in the denominator of the exponent. Okay. So that term I am just denoting it by sigma x. Okay. I am going to denote the term by sigma x. Okay. Okay, I'm denoting it by sigma x square. Okay, I'm just using the symbol sigma x square. Okay, so for now, we'll see for various values of sigma x, how does this graph behave? Okay. So for sigma x equal to 1.5. Okay, so now in the initial case, what is the value of sigma x? So in this function, the value of sigma x is 1 because the denominator other than 2, the denominator doesn't have anything, so it is equal to 1. So for sigma x equal to 1.5, we just observe what happens to the graph. Yes, so this is a new graph for sigma x equal to 1.5. Okay, so what is sigma x? Sigma x is the term that we have added in the denominator. Okay, so for a value of 1, we saw the previous graph. For sigma x equal to 1.5, the graph is slightly expanded, right? So compared to the previous graph, this graph is slightly expanded, right? So now again I'm changing that value of sigma x to a still higher value. So now I am converting sigma x to 2. So what happens to this graph? You just observe what happens to this graph when sigma x equal to 2. Yes. So as you can observe, the graph is even more expanded, right? So now we'll see what happens if we decrease sigma x to a value which is less than 1. Okay. So I'm taking sigma x value to be 0.5. Okay. Now if I plot for this value of sigma x in the denominator, see what happens. What happened to the graph? It has become more narrower, right? So compared to the previous graph, it has become more narrower. Okay, so essentially what we are observing is the location of the graph. So we have a bell-shaped curve. Okay, the location of the bell-shaped curve, that is in the x-axis where it is located, whether it is located here or here or here. Okay, so whether the bell-shaped curve is here or it is here or it is somewhere else like this here. Okay, so these locations are decided by the constant ax, right? So how broad is the curve? That is decided by the constant sigma x, right? So that is the conclusion by observing the previous graphs. Okay, so basically what we are trying to tell is AX it decides the location of the maximum value of the graph. That is the bell-shaped curve, which we call it as a Gaussian density function. Okay, so the sigma x constant decides the spread in the density. That is, it decides the breadth of the graph. Okay, so how expanded or how contracted the graph looks, that is decided by sigma x. So Ax decides the maximum value of the peak. Okay, so these are the important terms in the function Ax and sigma x. Okay, so this constants Ax and sigma x, they have some specific meaning. So that we'll see later on when we study about expectation. Okay, so these are the topics that are coming later on in this chapter. Okay, for now you have to observe that these two constants control the behavior of the graph, right? So the constant Ax decides where the graph is located on the x-axis, whether it is located near to the origin or far from the origin. Okay, so the sigma x constant decides how narrow is the graph. Okay, yes. So now we see what are the applications of this Gaussian density. Okay, so this Gaussian density, it has a very large number of practical applications. Okay, it is also called a normal density. Okay, so the other name for Gaussian density is a normal density. Okay, so it finds applications in many areas of science and engineering. Okay, so if you consider the most important topic in probability theory, then I will say the Gaussian density is the most important topic. So, okay, this we have discussed even in the very first introduction class, right? So the Gaussian density, the concept related to Gaussian density function, it comes in almost all the fields that you are going to study. Okay, so in electronic communication, okay, so communication theory and antenna theory, whatever you study, this Gaussian density function will play a very important role. Okay, so it is also, the other name for the Gaussian density is called normal density. It is also called a normal density function, or it is sometimes called a normal curve. Okay, so I have shown here some other applications of this Gaussian density. Okay, so this function is used to model thermal noise in resistors. Okay, so thermal noise means it is a randomly fluctuating voltage across a resistor. So if you are using a resistor in, say, some kind of an amplifier circuit, so obviously the resistor will have some noise voltage across it. Okay, so if you see the voltage across the resistor in an oscilloscope, you will observe this kind of a waveform. Okay, so you can observe this kind of a waveform if you just put the oscilloscope probe across the resistor. Okay, so sometimes these kinds of waveforms are seen. Okay, so these are called random waveforms. Okay, so if you model the amplitude distribution of these waveforms, okay, so here you can see the y-axis is voltage. Okay, so there are various voltages listed. Okay, so here you can have 0 volts. Here it is around 0.02 volts, 0.4 volts, etc. Like here it is minus 0.2. So if you calculate the number of times this particular voltage occurs, okay. So if you calculate the number of times the zero voltage occurs, okay. So along this line, how frequently is the voltage lying within this range? So if you plot that as a frequency curve, you will get the highest number of voltage levels will be present near the 0 voltage level. Okay, so if you slightly move upward towards the positive voltage, say 0.01 volts, so how many times you get 0.0 volts? So that if you plot, so again you get this much graph. Okay, so say go to the negative side, say minus 0.01 side, so how many times the voltage touches this level? So if you plot put a frequency plot, you will get like this. Okay, so like that you can see the entire range of voltages, and then you can plot some graphs here. Okay, so finally what you get is a bell-shaped curve. Okay, what you get is a normal distribution curve. So in any study of thermal noise in electronic systems, you will be using this Gaussian model. Okay, and there are other applications in manufacturing. Okay, so whenever you manufacture some component, and the component has a particular parameter related to it. Okay, so suppose say you have a manufacturing of say a vehicle wheel. Okay, so a bike wheel. Okay, so the wheel has a parameter called diameter, right? So a wheel has a diameter. So when in a manufacturing process, there will be some process variations which will create some variations in the diameter. Okay, So if you plot the variations in diameter, again you will be getting a Gaussian curve. Okay, so this Gaussian curve occurs naturally in many applications. And very recently, if you observe the news related to COVID-19, so you can see a lot of curves like this. Okay, so this is actually I have taken this from a newspaper clipping. Okay, so the time since first case. Okay, so the x-axis represents the number of days. Okay, so starting at the start of the pandemic, there were very less number of cases, and at some point it peaks, and then after that the pandemic reduces in number. Okay, and you can see two different curves. Okay, so the first curve is without any protective measures. Okay, and the second curve is with some protective measures. You can see it has a very flat curve. Okay, so this is what we hear in the news. Okay, so flattening the curve. Okay, so the y-axis represents the number of cases. Okay, so in whenever you do some population studies, again you will encounter a lot of Gaussian curves. Okay, so whatever curve we are seeing here, this is also a Gaussian curve. Okay, so the Gaussian curve, it actually does is it models various things in real life. Okay, the Gaussian curve. So this function is very important function which models a lot of real life phenomena. Okay, so we can even say that it is modeling the pandemic. Okay, okay, so this is the importance of Gaussian density function. Okay, so using this function we'll be finding out some probabilities, because obviously density represents the density of the probability of some particular random variable. Okay, so what is the main application is we can find the probability of some particular events occurring through the use of the random variable. Okay, so this again is the review of the properties of density function. So as you can see, density function is nothing but the derivative of the distribution function. Obviously, the third property states that the distribution function can be obtained as the running integral of the density function. Okay, so this is the third property. And we also know that the integral of the density is equal to 1, and the density is always greater than 0. Okay, so if we want to find the probability of the random variable lying between two limits, we have to integrate the density between those two limits. Okay, so what we are observing here is, so when we are calculating probability, so definitely we need an integral of the density function. Okay, and then if we want a distribution function, actually the distribution function itself, this a capital Fx of x is itself a probability, right? So it represents the probability that the random variable x is less than or equal to some particular value x. Okay, so this is the probability represented by the capital Fx of x. Okay, so whenever we are in need of this quantity, like probability of the random variable being less than or equal to some particular x, we can directly evaluate this Fx of x, which is the distribution function. Okay, so we'll see in the next slide how this distribution function is evaluated. Okay, so as you can see here, it is nothing but the integral of the density function, but this integral has some limitations. So that is what we are going to see in the next slide, and how we are overcoming the limitations, that is also seen. Okay, okay, so probability distribution is related to the density by the integral. It is a running integral where the upper limit changes continuously. That is, the upper limit is x, and we have an integration variable here which is denoted by zeta. Okay, so this zeta is the integration variable. Okay, but the function here is actually the density function of x. So you can observe the upper limit is x. So this is a running integral. Okay, so now instead of this small fx of x, we are going to substitute this function here. Okay, so sorry. So yeah. So in the integral, what we are doing is we are substituting the Gaussian density. Okay, so this is substituted for this fx of x. So along with this constant term in the denominator. Okay, so what we get is the distribution function capital Fx of x. Okay, so the capital Fx of x represents what is known as the general Gaussian distribution function. Okay, so what we have actually done is This is the original definition of fx of x. Right? In that definition, for the small fx of zeta, we have substituted the entire term from our very first slide. Right? So we are using the exponential and the denominator term to root of 2 pi sigma x square. Okay. So the problem with this integral is that it has no closed form solution. Okay. It has no known closed form solution. By closed form, what we mean is, see, when we solve this integral, we cannot reduce it to some kind of a function of x. Okay, we cannot reduce it to say some kind of say x square plus 1. Okay, we cannot reduce it to simple terms in terms of x. Okay, so this is not, or any other function of x, say some say g of x. Okay, so we cannot reduce this integral to a simple function of x. This is not possible. Okay, so this kind of integral is called as improper integral. Okay, so these are very weird kind of integrals which we cannot evaluate. Okay, so only possibility to evaluate this integral is using some approximation methods. Okay, we have to numerically do this do that integration using some approximation methods. Okay, so already this methods are used, and then there are standard tables available for this integral. Okay, so this integral can only be calculated numerically. Okay, so we cannot use mathematics to find the integral. We can use the mathematics, but it is called approximation methods. Okay, so we cannot use the standard calculus methods to find out this integral. Okay, so we are using something called a tabulated form of this integral. So why we are finding this integral? So first of all, what is the need to find this integral? So can anyone answer? See, I'm saying that we are finding out this integral. So what is the need to find that integral? Why do we find fx of x? What is the use of finding fx of x? Can anyone tell what is the use of fx of x?
To find the area covered.
Yeah, it is area covered. Okay, so it is nothing but it is the probability of, so the fx of x gives the probability that the particular random variable x is less than a given some value x. Okay, so less than a constant value x naught. Okay, so that is the importance of this integration. Okay, so I think Anil sir wants the class. Okay, okay, I'll continue till 4 p.m. Okay, there's a message. Just a minute. Okay, so we'll continue till 4 p.m. Anil sir, I've informed Anil sir. Okay. Yeah. Okay. So this integral is useful in finding probabilities. Okay, probabilities of events such that the capital X is less than some particular small x. Okay. So the main use of this is finding out probabilities. Okay. So now to numerically evaluate this function capital Fx of x, if you consider this function, if you observe this function, we have two constants here, right? Okay, we have two constants, ax and sigma x, right? So how many combinations of those constants are possible? If you observe this function, that is the distribution function. So it is so it is 1 by root of 2 pi sigma x square integral minus infinity to x e power minus zeta minus ax the whole square divided by 2 sigma x square d zeta, right? So now if I want to numerically evaluate this, I should know the particular value of ax and sigma x, right? So for different Gaussian distribution functions, the ax and sigma x will be different. Okay, so there will be infinite combinations of ax and sigma x, right? So maybe in one particular model I'll have ax as 5 and sigma x as 2. Okay, in another model I'll have ax as 10 and sigma x as 1. Okay, so there can be different combinations, so the combinations are infinite. Okay, so we cannot go on creating tables for all the combinations of ax and sigma x. Okay, so it is very impractical. So what we do is we do something called normalization, which corresponds to the case where ax equal to 0 and sigma x equal to 1. Okay, so when we plot the graph for ax equal to 0 and sigma x equal to 1, what we say is we say the graph as a normalized Gaussian function. Okay, so this process is called normalization. Okay, so when we create this function fx of x for the case ax equal to 0 and sigma x equal to 1, okay, such a Gaussian function where these conditions are true, this and this are true, okay, that kind of a Gaussian function is called a normalized Gaussian function. Okay, you should not confuse this normalized with the name normal. Okay, so that is different. So previously we said that the Gaussian function is also called a normal distribution, right? So that is different and this is different. Okay, so normalization is not same as normal. So these are not same. So many times people have this confusion. Okay, this is called a normalized Gaussian distribution because we are simplifying the case, right? We are simplifying this entire function by putting ax equal to 0. So we are eliminating this term and we are going to put sigma x equal to 1. Okay, we are simplifying that. So once we have simplified that by putting these two constants, so what we obtain is this function. Okay, so this is the thing we get after simplifying, right? Putting ax equal to 0 and sigma x equal to 1. Okay, so just compare this and this. Okay, you can compare this function and this function. It is obtained by putting these two, substituting these two values for ax and sigma x, right? So since this function is a simplified version, we represent it with a different symbol. We just use capital F of x. Okay, we drop the suffix x. Okay, the suffix is dropped here. Okay, so you can observe the suffix capital X is dropped here. So this is the simplified version. Okay, so this function is what is called the normalized Gaussian function. Okay, so now whenever we are making a table, we are going to plot just the normalized Gaussian function. Okay, so only the graphs are plotted, the tables are calculated only for the Gaussian, normalized Gaussian function. Okay, so then we'll see how plotting the normalized Gaussian function helps us in finding the values for general Gaussian function like this fx of x. Okay, so they have a very simple relationship by which we are using the normalized Gaussian function for any kind of Gaussian, for calculating probabilities related to any kind of a Gaussian random variable. Okay, so now we'll see how the values are given in the tabular form. Okay, so this is called the normalized Gaussian distribution table. Okay, so this is a standard table available. It is available at the back of your textbook. Okay, and also you can download it from the internet. Okay, so this is a very standard table which is used in a lot of industries. Okay, so a lot of applications use this table. Okay, so here you can see the plot of the Gaussian curve, and here you can see that the Gaussian curve is centered at the origin. Okay, the peak occurs at the origin, right? And then the values from -3 to +3 are shown, right? So you can see here at the left column of the table. Okay, so there are some numbers listed, right? So we have numbers ranging from 0 to 3. Okay, so these are the numbers that are shown in the leftmost column of this table. Okay, and then on the top row, you can see there are some decimal numbers, right? Okay, so so there are some decimal numbers shown on the top, and there are also some decimals and some real numbers shown on the leftmost column, right? So this column. So now these are values, the values present here. These are the values that are numerically calculated for f of x. Okay, not the fx of x. It is calculated for f of x. Okay, so just go back to the previous slide. So these are the values calculated for this f of x. Okay, these are all values of f of x at various locations along the x-axis. Okay, so the locations along the x-axis are listed in the leftmost column. Okay, so this column represents various locations on the x-axis. Okay, so the numbers here, so these numbers, they represent the probabilities, right? So okay, so they represent the probabilities of capital X being less than particular location in the x-axis. Okay, so you are observing a curve here. Okay, on the right side you are observing the curve. So what does that curve signify? The curve shows the capital f of x. Okay, it is the plot of capital F of x. Okay, so actually it is nothing but all the numerical values are plotted in this graph. Okay, so all the values that you encounter along the y-axis. Okay, so these are the values. Suppose you take x equal to 0, you have a value of 0.5. Okay, okay, so here it is showing a different graph. Okay, so all the values along this okay, it is here, it is actually showing a shifted version. Okay, we'll just consider the form of the graph. Okay, so all the values shown here are used to plot this graph. Okay, this is the graph of fx of x. Okay, so how is the graph, how are these values obtained? These are obtained by integrating. These are obtained by the running integral, right? So the running integral is shown in the red colored shaded region here. So the shaded region shows the running integral, and you can also see the running integral here, right? So only thing is here I'm showing the different notation for the density. Otherwise, the meaning remains the same. Okay. So p of capital X less than or equal to small x represents this one, fx of, sorry, the f of x, right? Okay. So now if we suppose I am asking the question, what is f of 1.57? Okay, so how to find this value? So f of 1.7 is nothing but the probability that the capital X is less than or equal to 1.57. So what we have to do? So 1.57. Okay, I'll just change my highlighter to a different color so that you can understand better. Okay, I'll use the pen. Okay, so 1.57, where does it lie? So it lies somewhere here, right? So along the x-axis, 1.57 lies somewhere here. So you have to integrate the area starting from minus infinity up to this line. Okay, so we'll be including all the area that is shaded red here. Okay, so that value is given in this tabular column. Okay, so how to find that value? So along the leftmost column, you go to this point. Can you see 1.5 here? Okay, so in the leftmost column, go to 1.5. So on the top row, choose 0.07. Okay, so look at the value that is at the coincidence of these 2 points. Okay, so if you come along these 2 points, so this is the value that you get here. Okay, so the value is 0.9418. Okay, so f of 1.57 is read from the table as 1.5 along the leftmost column and 0.07 on the top row. Okay, so the number that corresponds to that that f of 1.57 is 0.9418. Okay, so this is equal to 0.9418. Okay, so this represents a probability, right? So this value represents the probability of x less than or equal to 1.57. Okay, so this is the method to read the graph, read the table. Okay, so is that clear how to read the table? So anyone, can you give me a reply? Is it clear how we
Yes,
are
sir.
reading the table? Yes. So whatever number is given inside this f, inside this capital F function, so that number, the first the non-decimal part is the integer part, and the next first decimal point is read from the leftmost column, and the next decimal digit is read from the topmost row, and then the coincidence is read as the probability. Okay, so like that you can observe here all the values start from 0 to the 0.3, right? So actually the curve extends even beyond 3. Okay, so there are some applications where we need just up to the 0.3. If you want more than 3, you can, there are tables available for those values also. Okay, so sometimes the table will be extended up to say maybe 10, okay, up to a value of 10. Okay, so these are standard tables available, and you can refer to the appropriate table whenever you have been asked such a question. Okay, yes. So now we will see, this is all that we have seen is only for the normalized Gaussian distribution, right? But in practice or in practical problems, we will not be always getting a normalized Gaussian curve, right? So practically, we will be only getting a general Gaussian curve where the AX and sigma x will not always be equal to 0 and 1 respectively, right? So the AX will not be always 0 and sigma x will not be always equal to 1. So in that case, we have to have some method where we can use the results of the normalized Gaussian distribution to find out the probability of, say, the general Gaussian distribution. Okay. Okay. So for that reason, we are going to derive a relationship between a normalized and general Gaussian distribution. Okay. So now what we are seeing is, we are going to see what is the relationship between the normalized and the general Gaussian distribution functions. So this is our general Gaussian distribution function. You can see there are, the constants are present here, sigma x and ax. So here also we have sigma x. Okay. So in this general distribution, okay, so it is, the distribution is nothing but it is an integral, right? So integral of minus infinity until x, integral of e power minus zeta minus ax the whole square divided by 2 sigma x square d zeta, right? So now in this integral we make this substitution. So we create a new variable u, which is equal to sigma minus ax by sigma x. Okay, so what is du by d zeta? Sorry, I have said it as sigma, it is zeta. Okay, so u equals zeta minus ax by sigma x. So what is du by d zeta? It's a simple derivative. So just take the derivative of this one. So what you will be getting is simply, so it is d zeta by, so we will be only getting 1 by sigma x, right? So if you take the derivative, you will be getting 1 by sigma x. So you cross multiply d zeta here, so you will be getting du equal to d zeta by sigma x. Okay, so now we are since we are making the variable change in this entire function. Okay, so your d zeta will be sigma x into du, right? So you can just cross multiply. So sigma x comes here. So sigma x into du will be d zeta, right? So you substitute that for d zeta and you eliminate these values here. Okay, zeta minus ax by sigma x is nothing but u. Okay, so this entire term on the numerator, it can be replaced as u square by 2, right? So the 2 is separate in the denominator, so it becomes u square by 2. The negative sign appears unchanged here, so it is written as e power minus u square by 2. And then if you observe the limit here, it is x, right? So when zeta is equal to x, what is the u value? So here we are integrating with respect to zeta, so the limit is x. Okay, so when zeta takes the limit of the value of x, which is the upper limit, your u will take the value of x minus ax, right? So that is why we have changed the limit to x minus ax by sigma x. Okay, and then there is a sigma x square in the denominator, so that becomes sigma x if you eliminate the root. Okay, and then here you saw d zeta is equal to sigma x into du, right? So we have a sigma x here. Okay, and then we also have a sigma x in the numerator. Okay, which comes from this place. right? By the derivative, there is also a sigma x in the numerator, so they both get cancelled. So we have 1 by root 2 pi integral minus infinity to x minus ax by sigma x into e power minus u square by 2 du, right? So this entire expression, I'll just use my eraser so that everything is clear. So is it clear until this point?
Yes, sir.
Yeah. So what you have done is we have just made a substitution. Okay, we have taken this entire integral. Okay, and then we have made this substitution u equals zeta minus ax by sigma x. Okay, so the same integral we have rewritten in terms of u, right? So we just made a simple substitution here, and then we have rewritten the entire upper integral into the simpler lower integral. Okay, so this entire integral here, which is an integral happening in terms of zeta, that we have replaced by a simple integral here. Okay, which the integration variable is u. Okay, which this occurs through the substitution. Okay, now you compare this integral with the previous definition of our normalized Gaussian distribution. Okay, so in the previous slide we saw what is a normalized Gaussian distribution, right? The normalized Gaussian distribution is nothing but a Gaussian distribution where it is the same thing, right? So it is the same thing where the sigma x and ax have become 0, right? So this okay, so sigma x has become 1, so this we have put it as 1, and the ax becomes 0. Okay, so that will give you your normalized Gaussian distribution. Okay, so now if you compare this and this, okay, so you compare this with this, so what do you observe? Are they looking the same? Functionally they are looking the same, right? See, this we obtained by substitution. Okay, so from here to here we came by this substitution. From here to here we came by which substitution? Ax equal to 0. Okay, so that normalizing operation we came here by normalizing up, and sigma x equal to 1. Okay, so we came here by this normalizing operation, but here from here to here we came by this substitution operation. But now we observe that this and this are same, right? So this one is same as this one. Only thing is they are written in a different form, right? So here in place, see, only the variables are the symbols are different. It is written in terms of u. Here it is written in terms of zeta. Okay, so one more difference is, so here we have x minus ax by sigma x. Here we just have x. Okay, so comparing these two, what we can say is, so the normalized distribution, when it is shifted by the amount ax and then scaled by 1 by sigma x, what we get is the general distribution fx of x. Okay, so can you compare these two and arrive at this value, this relationship? Okay, so this fx of x is nothing but it is the shifted and scaled version of your normal distribution. Okay, so the general distribution fx of x is nothing but shifted and scaled version of your normal distribution. Okay, so this is the important relationship here. Okay. So hope you are able to understand this relationship. Okay, so this is the relationship we want between the normal distribution, okay, the normalized normal distribution or the normalized Gaussian distribution and the general Gaussian distribution. So this is a very important relationship. Okay, so this is the normalized Gaussian distribution. This is the general Gaussian distribution. Okay, so they both are related by just by a shifting and scaling operation. Okay. So now we'll see how to use this concept in say how to use this concept in calculating the probabilities. Okay. So again, we'll take the help of the table to calculate these probabilities. So what I will be doing is, okay, so we'll see in the next slide what are the problems, what kind of problems we'll be encountering while doing the calculation of probabilities. Okay. Okay, so I just summarized. So the value of a general Gaussian distribution function at any value of x can be evaluated using the tabulated values of normalized Gaussian distribution. Okay. Okay. So now we have a simple example. Okay. So the example says that it asks us to find the probability of the event x less than or equal to 5.5. Okay, for a Gaussian random variable having ax equal to 3 and sigma x equal to 2. Okay, so we have some general Gaussian random variable. Okay, so ax equal to 3 and sigma x equal to 2. So how does the function look like? So can you visualize such a Gaussian random variable? So how does the density function look like? So if you want to plot the density function, which is small fx of x. So how does the where is the bell shaped curve located? Yes, where is the bell shaped curve located for this particular case? Can anyone answer?
3.
Yeah, it is located at 3. Very good. So at the point 3, the bell shaped curve moves and stands at the point 3. Okay, so sigma x equal to 2. Sigma x represents the spread of the curve. Okay, so we'll see how to check the spread of the curve. Okay, we'll just for now we'll just say that. So usually the curve is lying at the origin. Now it has moved from the origin to the point 3 because of ax equal to 3. Okay, so sigma x equal to 2 represents the spread in the curve. So how broad it is. So that is given by, that is decided by the sigma x. Sigma x equal to 2. Okay. So now we are asked to find out the probability of capital X being less than or equal to 5.5. Okay, so where does 5.5 lie? So here is 3, maybe here we have 4. Okay, so maybe here we have 5. Right, so 5.5 lies somewhere here. Okay, so please note that the curve does not touch 0 immediately. Okay, it is asymptotically going to 0. Still there are some positive values even after 5.5. So I assume that 5.5 is somewhere here. Okay, so even beyond 5.5 the curve is extending. We want to know the even here also below 0 also the curve is extending. Okay, so I want to find the probability of x less than 5.5, capital X less than 5.5. So how do we find that probability? It is nothing but the area of this curve, which is formed from this closed figure. Okay, so which is under the curve until the point 5.5. Okay, so this entire area is what we want. Right? So we are asking this entire area. Okay, so by p of x less than 5.5, what we mean is we want the value of this entire area until this line, which is equal to 5 x equal to 5.5. Okay, so by definition of fx of x. Okay, so if you go back to the definition of the distribution function. Okay, so this fx of x is nothing but it is the probability of some random variable being, okay, I just made a mistake here. It is less than, right? It should be less than. Yep. Yeah, sorry, there's a mistake here. Just I'll change it to this less than. Okay, So probability of x less than 5. So this I just make it clear. This is probability of x less than 5.5. Okay, so probability of x less than 5.5 is equal to fx of 5.5. Okay, so this represents the small x. So 5.5 here represents the small x, right? So now we want to find this area. Okay, so this is this a normalized curve or a general Gaussian curve? So this curve, this bell-shaped curve, this is a general curve, right? So this is a general Gaussian curve. Okay, but we have table values only for the normalized Gaussian curve, which always lies at the origin. Okay, so a normalized Gaussian curve only occurs at the origin, right? It's a bell-shaped curve which is lying at the origin at 0. Okay, so now we know only area for this curve. Suppose this is the area. We know the area for this curve which is listed in the table, but we don't know the area for this curve. Okay, so how do we use this area of this curve to this curve? What do we use? The relationship between, yeah, the same relation. So the relationship between the generalized distribution and the normalized distribution. Okay, so now we know the value of ax, which is equal to 3. Then we know the value of sigma x, which is equal to 2. So we find fx of 5.5 as f of 5.5 minus 3 by 2, which is equal to f of 1.25. Okay, so now f of 1.25 can be read from the table. So if I go back to the table, we want f of 1.25. So here I have 1.2. Okay, so here I have 0.05, right? So they both overlap at this point, right? So this is 0.8944. So that is what is my result. Okay, so what we obtain is 0.8944, which represents the probability that the value of x is less than 5.5. That is, the random variable x takes a value less than 5.5. Okay, so this is our final answer for the probability of this particular event. Okay, so with this we come to the end of this session. So what I actually wanted to stress is the importance of the Gaussian random variable. Okay, so the Gaussian random variable finds a lot of application. Okay, so the entire probability subject itself is very useful because of this Gaussian random variable. Okay. So this I have represented as a final solution. Just making it clear. So P of, again I made a mistake here. Here also this is P of x less than 5.5. So please note the changes here. This P of x less than 5.5, not greater than. I'll make those corrections in the slides that are shared in the stream. P of x less than 5.5 is equal to 0.8944, which we get from the table. Okay, well, with this I end the session. I just want to know whether there are any doubts, or did you understand the concepts today? So maybe we are a little bit vague here. Okay, so you go through the slides. Okay, so go through the slides again and again, and then only then you will be understanding what is a Gaussian distribution, what is a Gaussian density. Okay, so how this Gaussian density is useful. So what are the applications of this Gaussian density? Okay, so was that clear to everyone? Have any doubts? So what we have seen today is only the Gaussian density, which is a continuous, which is a density function of a continuous random variable. Okay. So important thing to remember is that a Gaussian density is defined only for continuous random variables. Okay, and then the distribution function that corresponds to the Gaussian density, it is difficult to evaluate using a closed form expression. Okay, we evaluate it only using some numerical approximation methods. Okay, so those values are listed as a tabular form. Okay, so we use a standard Gaussian distribution table to evaluate various probabilities relating to different events which are specified as points along the x-axis, okay, which are specified as maybe a range of points along x-axis. Yes. Okay. You can stay back. I'll take attendance. Step back. Take some snapshots. Okay, I've taken the attendance. Okay, so you please go through the slides because these concepts are a little bit difficult to understand. Okay, so revise properly. Okay, now you can leave the class. Okay, so you can go for the next class, Nils's class.
Thank you, sir.